Welcome to EE World. I'm Senior Technical Editor Martin Rowe. Serial data streams are a challenge for engineers, especially if it's something that you're not used to dealing with. If you're not used to dealing with 10 gigabits per second or higher, and they can go much higher, this may be a new field for you. And you have to simulate your transmission channel, because if you're sending this data over copper, as we all know, copper is lossy. It's kind of like putting your signal through a low pass filter. Some of the high frequency signals will get lost, and that can create bit errors. And what really matters in serial data is bit error ratio or bit error rate, depending on which school you come from. And the equipment, the software to simulate some of that uh, copper can get expensive. But fortunately, there's a free version out there. And the free version was created by David Banas, who we have here, along with several others. And his list of contributors looks like a who's who of signal integrity. And we're gonna talk with David a bit about the software that he's created called pyBERT. And it is a free software. We will provide the links in the accompanying article with this video. And so, David, welcome to EE World. And so, tell us what was the um, impetus for creating pyBERT?
Thank you, Martin, and hello, everyone. And thanks for spending this time with us. I know your time is valuable, and I appreciate that you thought this worth its while. So, Martin, the answer to your question is it goes way back to my Xilinx days, early 2010s, and I was making the transition from supporting parallel interfaces to supporting serial interfaces. And my peers and I were finding it really difficult to get time on the simulator because, as you noted, they are very expensive. And companies typically employ a very small number of licenses to them, which means if you go in and say to the lab manager, hey, I'd like an hour to play with this thing so I can learn how to use it, you often get laughed out of the lab because he's got a long list of much more legitimate use requests for that tool. And I'm a firm believer that we learn best when we play. And so what I realized is that the rest of us need a toy that we can play with while the real thing is being used, for the business to make money. And so that's why I set out to make pyBERT. I wanted us as a community to have a toy that we could play with, that no one would tell us, hey, this thing's too expensive for you to just play with. You need a good reason. I wanted people to be able to just play with something so that they could learn about serial links.
Well, that sounds like a big project, and we'll get to the logistics or the mechanics of pyBERT in terms of what you need to get it. It is freely available, and we'll talk a little bit about the installation process a little later. But first, let's talk about the uses. So, serial data streams have to travel over copper and of varying lengths. It could be cables, it could be backplanes, it could be just traces on a board. And you need to be able to simulate that so that you know what the transmitted signal is going to do when it reaches the receiver. And it can get quite distorted, especially as the speeds go up. Now 112 gigabit per second is getting common. It's certainly in use. 224 is in development, and engineers are using various speeds below those, depending on the need, depending on the need for the amount of speed, whether it's 56 or whether it's lower like 28 and so on. So what what do you do with pyBERT? What kind of information do you need to be able to simulate a channel? And I know you have a demonstration available, so if you'd like to switch over to your screen, let's talk about what kind of information you need to put in, and what it will tell you from the simulated signal that it provides. So we're entirely in a simulation world here, as far as I understand. We're not taking any real data and analyzing it. We're just, as you said, playing around. So why don't you share your screen and take us through what pyBERT does?
Okay, will do. So, as Martin mentioned, uh, when we're going to simulate a link, a serial link, we have to know something about the channel that we're wanting to simulate. That is to say, the medium that connects the transmitter to the receiver. Uh, in pyBERT, we can define that one of two ways. pyBERT has a native model. Martin, can you see my mouse pointer when I move it around like this?
Yes, we can see
Oh,
it.
wonderful. Okay. So these parameters here are used to configure the native channel model that pyBERT includes, which actually comes from Dr. Howard Johnson. In his first book, High Speed Digital Design, he offers an analytical model of what's called unshielded twisted pair. And this is the old-fashioned telephone wiring that we all have, well, not all of us anymore, but a lot of us still have running through our homes. It's just a twisted pair of copper wires that typically 28 gauge, and they have no shielding around them. And so pyBERT's native model of the channel is just that. It serves as a real good worst case scenario for serial link design. You'd almost never use it for a serial link design, but it can establish a wonderful worst case bound for your link. So that's one option. But a much more commonly used option, pyBERT, is to take the alternative, which is to load in a touchstone file. This is a file that contains a lot of S parameter data about a particular channel. I don't know if I have one or not. I only brought this box up to show you that a file could be selected, and I won't go any further down this path because I don't think it really has much ROI. The point is that you have an alternative to pyBERT's native model, and that alternative comes in the industry standard form of a touchstone file.
And where do those touchstone files come from?
Those touchstone files, they have two sources. They can be completely analytically generated, but more commonly, they're simply measured with very, very expensive and precise machines called vector network analyzers, which are made by companies like Agilent and Roden Schwartz uh, uh, and Tektronix.
I think you meant Keysight.
Yes, thank you. I did mean Keysight. Thank you for the correction.
Okay, we'll go on.
Oh, okay. So those are the two options for channel modeling in pyBERT. You also have options for modeling the transmitter and the receiver. Again, pyBERT offers you a native model, which is fairly simply parameterized here and here. But you also have the option to import what are called IBIS AMI models. And again, we just open a file dialog. I won't go any further down the path because there isn't really much ROI in that. The point is, if you have what's called an IBIS AMI model of your transmitter or your receiver, then you are able to use that as an alternative to pyBERT's native models.
I see. So if once you have this model in place, whether it be one of the native models or a native model that you've modified, because I can see you've got some places where you can change the parameters, or
That's right.
whether it's so wherever the source of the channel model comes from. Once you have it, then you have to give it a signal and see what will come out the other end. So
That's right.
let's look at the top section there,
Okay.
what you call simulation central. And as you can see, it's set up right now for a 10 gigabit per second link, but you can change that. You may be able to see that the cursor is flashing, and you've got, I believe it's 8,000 bits.
Yes.
And then you've got something below that, which you call NSPB. What is that?
That's the number of samples per bit. So we'll be running a vector of floating point values through the simulation signal chain. And what we need to specify is how many of those vector elements are used per unit interval or per bit.
Okay. And then you've got modulation, and it looks like you've got some choices. Now, the most popular one is NRZ, which is non-return to zero, simply a high and a low. And of course, that amplitude will depend on the voltage of your signal. But you've got
That's right. Yeah.
then you've got another one called PAM4, which is essentially NRZ. Instead of having two levels, it has four levels.
Yep.
And in that case, each level represents 2 bits.
That's right.
And then you've got duo binary, which is not as popular. Can you just give us tell us a bit
Yeah.
what's duo binary?
Yeah. Dual binary is an interesting one because it belongs to a family of something called partial response signaling schemes, where you actually are using the imperfect response of the channel as part of the modulation scheme. You're counting on it in order for the modulation scheme to work properly. It's a really clever scheme, and it's been really popular in academia for many decades now, but it hasn't really caught on in industry. Industry sort of skipped over it and went straight to PAM4. I think probably because um, they see that eventually we're going to need PAM4 anyway, and because sometimes dual binary is difficult for people to really grok and really understand completely. You know, if you haven't gone all the way to a PhD in communication theory.
Okay. And moving over to the next set, so you've got something that you call do sweep. What is that?
Oh, um, so a lot of times, the way the typical design flow goes is you'll try some equalization settings, and we'll get to those, I'm sure, in just a moment here.
Mm-hmm.
You'll try some settings, you'll see how well the link works, and then you'll want to come back around and fiddle with those a little bit. And it's a very incremental and very iterative process. And so one thing that a lot of these tools do is they automate that iteration for you. And that's what pyBERT does if you turn on the sweeping. It then allows you to define several different combinations of parameter values that you want run. And then you can go away and have a cup of coffee and chat with your colleagues while pyBERT just cycles through all those and prepares the results for you.
Okay. And then you've got a choice of bit patterns that you can simulate. You've got PRBS, that stands for pseudo random bit sequence, and you've got the 7-bit version, the 15-bit version, the 23-bit version.
Yeah, those are just those are the three most common used in
Mhm.
serial com. That's why we've coded them up.
Sure. And for this, I think that's probably all you need. That pretty much does cover everything. And then you've got a few other parameters. And so once you've got everything in place, what's the next step? What do you do
Well,
next?
you run the simulation. And to do that, you can come up here to the simulation menu and drop it down and select run. And of course, there's a keyboard shortcut that you can use as well.
Mm-hmm.
So I'll click here now. And if you look in the lower left, you can see pyBERT telling us, oh, it's done. It goes pretty fast on this machine. This is one of those zippy new MacBooks with the new Apple Silicon. Um, but if you happen to have caught it, you'll notice that this status indicator took you through several phases of simulation. But it's finished now. And what we can do is we can look at those results. The results come in several different flavors. This screen is showing us how well the CDR and the DFE adapted to the signal. And this is a very strong and stable adaptation as adaptations go. The reason I'm saying that is because once we settle out from these initial bumps here, we don't ever see any more perturbances. So that's how we know the CDR locked on real solidly. And the DFE adaptation over here in the upper right, you'll notice that once it reaches a steady state, the only perturbances we see are the little 1-bit glitches that are always typical of digital systems. So it continues, the DFE always continues to hunt, but the fact that it is not shifting very far means that its adaptation is very solid. It's locked on to what it needs to be.
Okay. And for our viewers who may not know some of these acronyms, CDR stands for clock data recovery, and
Yes, my
DFE,
apologies. Yeah,
that's all right. And DFE stands for, if I'm getting this right, decision feedback equalization. Am I
that's
correct?
right. Yeah,
Okay.
that's
All
exactly
right.
right.
And so equalization is something that's used to compensate for the losses or the characteristics of the channel. So if you know that you're going to lose a certain amount of content, you can amplify it essentially
That's exactly
at the
right.
transmitter.
In fact, your characterization of the channel as a low pass filter was very accurate. The tab I'm displaying right now is the frequency response of the system taken at several different points. In the top left, we have the channel all by itself before we consider any of the equalization that we're applying. And as you can see, just as you predicted, Martin, it rolls off as we climb in frequency, just like a low pass filter would. And that is, in fact, what causes the distortion in the signal at the far end. And so what we're doing with equalization is we're basically just trying to counteract that high frequency roll off. And we do that by applying blocks or system modification components that actually have higher response in the high frequencies. And while the current situation doesn't show a very good exaggeration, we can fix that and we will when we run. You can see it quite well in the DFE. In this lower right box, the blue line is the frequency response of the DFE itself in isolation, and the red line is the cumulative channel frequency response after everything we're doing has been tallied up. And you can see what the DFE does. It has a frequency response that starts here just above minus 10 dB. And instead of rolling off at high frequency the way the channel does, it actually climbs. So it's actually boosting the high frequencies. And the result is that we get this little uplift in the channel just before the roll off. And the net effect of that is that it pushes out to the right the point at which the composite channel frequency response crosses some line. Minus 20 dB is a typical reference point used by serial comm engineers. And if you look at that point, in the raw channel, it crosses minus 20 dB at just above 4 gigahertz. So call it 5 gigahertz maybe. But in the equalized channel, if we look at where it's crossing minus 20 dB, we've pushed that out. You can see it's much closer to the 6 now than this one. This one crosses closer to the 4, and this one has been pushed out. Now, it may seem slight, but don't forget we're looking at a logarithmic scale here, both horizontally and vertically.
And we're also looking at the model of the twisted pair wire.
That's right. Yeah, you can only do so much with the old telephone cabling.
Mm-hmm.
It's quite limited. Yeah,
So if
that's
you've
right.
if you've got a backplane or a trace on a board or a better quality cable, those cross points are going to be pushed farther out in frequency as well.
That's right. And also typically you'll have a lot of boost going on here with the TX preemphasis and here with the CTLE. CTLE stands for continuous time linear equalizer, and it is one of the equalization components that exists in the receiver, whereas preemphasis is an equalization component that exists in the transmitter. And right now, these are almost doing nothing. And in a real world scenario, they would be quite peaked here at the high frequencies. Both of them would.
Okay. And so now let's look at some of the results that we might have gotten. So why don't you click
Okay.
on the results and let's see what we get from there. Okay, so this. Oh, okay.
So the
So
most typical thing we look at in Serocom are the eye diagrams,
mhm.
because they give us such a great high level indication right away of whether or not we're on track. And here you can see clearly the power of that DFE. The DFE is a very, very powerful equalization component. And you can clearly see that it has, in fact, opened up what was a closed eye coming into it.
Okay, and for those who may not know what an eye diagram is, it's simply you take a set. I believe we used 8,000 in this case.
That's right.
you take those 8,000 bits and you overlay them on top of each other so that they're all kind of sort of, I'll say, synchronized in time.
Yeah, that's right.
And when you do that, then you can start to see differences in one as one bit goes by versus the other, which you can't see if you're just looking at them, in a a purely time domain plot, like you'd see
Yeah.
on an oscilloscope. But here you can see the overlays, and you can see how messy they are.
Yeah,
And
that's right.
you can't tell anything from that. You can't.
No, no, no. You would be hopeless to try and recover the
Mhm.
signal
And that's because
from this one over here. Yeah.
Mhm. And that's because the high frequency content has taken what started out theoretically as an infinite speed or zero time rise or fall, and because those high frequency components have essentially been filtered out,
Yep.
the the uh, the rising and falling edges are no longer vertical. They start getting, well, in that case, pretty well horizontal.
That's exactly right. Here, in fact, is the pulse response of the system at the same 4 points that we're showing the I or the frequency response.
Mhm.
That's consistent throughout pyBERT. The four quadrants of any of these tabs are always showing you the same point in the signal processing flow.
Mhm.
And you can see, ideally, what we would want here is a perfect rectangle whose width was exactly the unit interval. And you can see that that is not at all what we get from this old telephone wiring. You can see that the energy of this pulse is spreading out into many, many of the adjacent unit intervals and causing what's called intersymbol interference, or ISI. So yeah, exactly what you were just describing, Martin.
Okay. So let's go back to that result. So the bottom right, we're seeing what looks a lot cleaner, and you can actually see the eye in the middle there
Yeah, that's
of
right.
that plot. And by doing so, um, the signals are cleaned up, and when you overlay them, you get this open eye, and that open eye is very important because the more open that eye is, the better your bit error rate will be.
That's right. That's
Okay,
exactly right.
and what you also get from one bit to another is the timing is not perfect. Even though that, yes, there is probably a pretty stable clock keeping things together. Nevertheless, it has what's called jitter from one, slight, very, very small differences in time from one bit to the other. When does it go high? When does it go low? How long does it stay high or low? All of those affect the
That's
opening of
right.
the
Yeah.
eye.
And
So,
jitter is such an important quantity to
mhm,
serial link design that we go into great detail in pyBERT to show it, again, following the same pattern of always showing the same point in the signal processing chain in these four plots.
mhm,
You can see how the histogram of jitter gets cleaned up dramatically by the DFE. Note that it spans the complete width of all of the three other plots, but once the signal is passed through the DFE, it's nice and contained, which is what we want. But jitter is a lot more interesting uh, in the frequency domain,
mhm.
or at least we're able to peer into its causes more acutely. Maybe is a better way to say that. And so we also give you a very detailed breakdown of the jitter in the frequency domain, and we separate it, which is crucial because the jitter that is related to your data pattern is dealt with quite differently than the jitter that is not related. And so it's very important to separate those two for engineers. And you can see we do that here. The data independent is in red, while the total is in blue. And then we try and actually tabulate the information for you to show you where you're getting the most bang for your buck in terms of equalization. So we try and show you among the equalization components, among the TX preemphasis, the CTLE, and the DFE, which component is really doing the most for you. And you can see that in this system configuration, the DFE is the clear winner in terms of rejecting ISI. It's providing us 6.3 dB of ISI jitter reduction, while the other two are giving us 0. And that's not their fault. It's because we have them turned way low. If we look at how we have this equalization configured, uh, you can see that we have very, very small values. Over here in the TX preemphasis, we only have the pre-tap turned on to begin with, and it's got a very, very small value. Likewise, we're only allowing the CTLE to boost 1.7 dB. That's almost nothing. So the DFE is really picking up the slack here. But when you're ready, I can demonstrate that there's some give and trade available there. But for now, I'll go back to your eye diagram.
Okay. So, uh, so you've got a lot of information here, and this can certainly help engineers to understand the different parameters in a transmission line, as far as as we saw on the initial screen. You can put in things like impedance, DC resistance, and so on.
Right.
And so you can play around with those and then see how that might affect the end result here that we're looking at. So
That's right.
let's move on and say, to how do you actually get pyBERT, and what do you need to install it? Let's look at the mechanics a little bit. And
Sure. Yeah, you bet. I'm going to pop over to a different screen to help everybody more clearly understand that.
okay, and what was interesting is you told me that you're running it on a Mac, so it doesn't run just on a PC.
Oh, no, it supports all three platforms, Windows, Linux, and Mac OS, and
Oh,
both
interesting.
flavors of Mac, the old ones with the Intel chips and the new ones with the ARM silicon, the M1, M2s.
Hmm.
Yeah. So can you see that okay, Martin?
Yes, we can see it. It looks like you've got a picture of a few contributors there. I recognize a
Yeah.
few faces, actually.
Yeah. So here's the pyBERT crew. These are all the folks that are helping to develop pyBERT. Clearly, there's yours truly. David Patterson is my main partner. He's really been driving the effort to keep pyBERT current with both the pyBERT 2, sorry, the Python 2 to Python 3 transition, as well as keeping our build infrastructure up to date with currently accepted best practices in the Python world. It's a chore that I'm just notoriously bad at. And David came and stepped in and just drove that. And I owe him a big, big thank you. So, David, if you're watching this, thank you very much. And please know that I really, really value the contribution that you have been making. Thank you, sir.
Okay, so it looks like you have this available on GitHub, as the links will point out. Uh,
Yeah.
so what do you need to download, and
Okay.
do you need to install anything on your PC, that, or your shouldn't say PC, but on your computer?
On your computer. Yeah.
On your
Yeah, you do.
computer.
And
Uh,
where
Go
and
ahead.
where you
Tell
can
us what you need.
Okay, and where you can find those instructions is in the instant gratification section of the wiki. So here we're at the wiki site uh, uh, for the GitHub project, and just in case any of you aren't familiar with that, you get to the wiki by clicking that right there. So you probably most often you come to the code page. I'll click on that so you can see what the code page for pyBERT looks like. So this is the most common place to land when you first enter the GitHub repository for a project. And what you want to do if you're wanting to install is you want to click on the wiki link here. I'm clicking now, and that takes you to the pyBERT wiki, which is where we have the installation instructions. They're called instant gratification. You can get to them by clicking right there. I just clicked. And here you can read all about installation and setup. There's a few preliminary notes, just kind of alerting you to certain things. And then you dive right in. You can see it says, in order to get pyBERT up and running on your machine right now, follow these steps. And you just follow these steps in order. And these have been worked through now for what, 8 years now, 8 or 9 years, and they are real solid and real foolproof. And we have not heard of any trouble with these, save for one very specific example, which occurred for two people quite recently and in the same way. And it turns out that when you do this first step, when you install the mini conda Python distribution, you do not want to do it as an administrator on your machine, and you do not want to do it for all users. So you're offered an option in the Miniconda installation to install it just for yourself, which does not require admin privileges, or to do it for everyone, which does require admin privileges. And you want to choose the first case. You want to install Miniconda only for yourself and do not request or do anything that requires administrative permissions. That's what got both of these two people into trouble recently. For everyone else, these instructions seem to be smooth as butter. People are typically up and running with pyBERT in like 15 minutes.
Okay, well that's great. Thank you for this tour of pyBERT and explaining what you need to download it and to install it. And it's good to know about that unusual
Yeah,
situation. That should help a lot of people. David, thank you so much for your time. I very much appreciate it, and I think our readers will too.
you are most welcome, sir. Thank you for having me.